And this is the Pima diabetes data set, which I'm sure you've all heard of it. This is where we look at the different features of a person and try to predict whether the person is suffering from diabetes or non-diabetes. That is what this data set is all about. Okay, so we're looking at the different diagnostic attributes of the person in terms of their pregnancy, blood pressure, uh, plasma levels, skin thickness, test, body mass index, pedigree, and age. And based on the different features of the person, we are trying to predict whether the person is diabetic or whether the person is not diabetic. We're trying to predict the class of the person. Okay, so I repeat again, based on the different features of the person, pregnancy, plasma, pressure, skin, test, mass, pedigree, age, based on the different features, we are trying to predict the class. The class is either class equal to 1, that means diabetes, yes, or class equal to 0, that means diabetes, no. That is what we are trying to predict. It's the binary classification we are trying to do. That's the idea. Okay. So first thing first, what we will do is we will, like, this is the data frame once again. So we have all the different features of a person. And based on the different features of a person, we are trying to predict, is a person diabetic, is a person not diabetic. This is the problem statement that we have. Now, in any machine learning problem, the most important part is to identify what are the most important predictors, what are the most important features. So, out of these 8 features, we are trying to identify which of these features are the most important features. So, we have total 8 features with us right now, and out of these 8 features, you are effectively trying to do feature selection. You are trying to identify which are the most significant predictors of the output class. Output class is ultimately what we are trying to predict. So we are trying to identify which are the most important predictors of the output class. So that is what we are trying to do. So feature selection in a way. So we use feature importances to kind of do this work. So this is what it is. So look at the different features of the person, and based on that, we try to predict whether the person is suffering from diabetes or the person is not suffering from diabetes. That is what it is all about. Right? And I think maybe here I can take a minute and try to clarify this also. What is the most important difference between regression and classification? Regression, we are trying to find out what is the line that best fits the point. I'm sure all of you can relate to that. So we have a lot of data points, X, Y combinations, and you try to find a line that best fits the points. So regression was all about best fit. Either it's a line that you're trying to fit or it's a curve that you're trying to fit, which is the case in polynomials. Because the patterns may not be in the form of a straight line. So either you try to find the line or best fit, or you try to find the plane of best fit or the surface of best fit. It can be a polynomial equation also. So that is the big picture idea of what we are trying to do in regression. Try to find out what is the surface that best fits the point. That's what we are doing in linear regression. Regression generally, it's a numerical output and it's a surface of best fit that you are trying to find out. Classification, you are trying to find out the surface of best separation. So what we are trying to do in classification, we are trying to find out what is the surface that best separates the classes. We have got red class, we have got blue class, the two different classes we have got, and we are trying to find out what is the line or plane or mathematical surface that best separates both the classes. That's what we are trying to do primarily in classification. So we have the blue class, we have the orange class, and in a classification problem, we are somehow trying to find out the class separation. We are trying to find out what is the line or plane or mathematical surface that best separates the blue class from the orange class. That's what we are trying to do. So
So can
if
you
I
repeat
have
that, sir?
to,
The difference between
I'll do that through
classification
a
and
I'll do that through
yeah.
a simple this thing. Because normally what we hear is regression is a number, classification is a category. That is just all that we hear. So numeric output we try to predict is regression, and categorical output we try to predict is classification. No, but I'm trying to give you a slightly more intuitive understanding of what classification actually is about. And it's also very important. Interviews they ask you questions like what is the decision boundary kind of thing. So look at this one. Look at the diagram. Again, what you're seeing in the bottom part, this is actually regression. So we have lots of X, Y combinations, and we are trying to find the surface that best fits the point. There are infinite such kind of surfaces you can create. A surface can look like this, like this, like this. And out of all the infinite number of mathematical surfaces, this is the surface that best fits the points. That's regression. So let's say we have the uh, speed prediction problem that we are trying to solve, Prashant. So we have the different attributes of the road condition, the steepness, bumpiness, and based on the different attributes of the road conditions, what we are trying to do, we are trying to predict the speed of the car. Okay. So based on the different attributes of the road conditions, based on the steepness, bumpiness, and other kinds of features, So based on all the different attributes of the road conditions, we are trying to predict what is the speed of the car. Will the car go slow or will the car go fast? That is what we are trying to estimate or predict here. That's the problem we are trying to solve. I repeat again, based on the different attributes of the road conditions, steepness, bumpiness, we are trying to predict should the car go slow or should the car go fast. Now, this is your typical labeled data for supervised learning. We have X, Y combinations. And so we are able to see that, okay, when the patterns are like this, the car is going slow. When the patterns are like this, the car is going fast. Again, when the patterns are like this, the car is going slow. When the patterns are like this, the car is going fast. So we have lots and lots of these so-called input, output, or X, Y combinations right now. So when the road is less steep and less bumpy, the car is typically going, uh, very fast. And when the road is very steep and very bumpy, it's a very steep and bumpy road, the car is going very slow. Lots of reds around here and lots of greens coming around here, right? So again, I repeat, lots of reds coming around here and lots of greens coming around here. So these are the slow and fast aspects that we are able to look at. So lots of reds there and lots of greens. Yeah, that's the way we are able to see. And what we are trying to do is we are trying to find a line or plane or mathematical surface that best separates the reds from the greens, right? So we have lots of reds here, lots of greens here, and we are trying to find out the line or plane or mathematical surface that best separates the reds from the greens. So there are infinite number of such surfaces you can create. Okay, so if you look at this particular two-dimensional mathematical surface, there are infinite number of such surfaces you can create. So we can create infinite number of such surfaces. And out of all the infinite number of such surfaces, we are trying to find out what is the surface that best separates the two classes. That is the surface of best separation that we are trying to get here. So we are trying to find out what is the surface of best separation. So these are lots of reds here, which are slow. These are lots of greens here, which are fast. So in this two-dimensional mathematical surface, these are instances where the car is going very slow. These are instances where the car is going very fast. So lots of slow, fast data points we have. And we are trying to find out the best separation between the slow and the fast. How do we best separate the slow from the fast? That is what we are trying to do. Okay. So out of all the infinite number of uh, surfaces we can have, turns out this is the best way we can separate slow from fast. In fact, that is what logistic regression does. If you see logistic draws a linear separation, linear boundary. Now, depending on the nature of the algorithm, the decision boundary will be different. If you use something like a random forest classifier, random forest will do something like this. It will be a non-linear decision boundary. So this is the crux of what we are trying to do in classification. You've got different classes. Here it is binary. There are two classes. And the model is trying to find the ideal separation between the two classes. So what you end up learning is basically this decision boundary. So this is the decision boundary that you're ultimately trying to create. And this is be some mathematical equation. In logistic, there is also a mathematical equation like probability sigmoid function. So this is what it is. This surface is basically that mathematical equation. That is the end result of what we are trying to do in classification. We are ultimately trying to find the best separation between the two classes. Right? I hope this is clear. Everyone's able to relate to it. The next time anybody asks you what is regression versus what is classification, answer it this way. Right? So try to intuitively explain the topic. And to connect the dots a little better for all of you, I can take you to one more diagram, which I'm sure you can relate to this a lot better now. I'll take you to one more diagram. I think you can relate to this a lot better now. Take a look at this, please. There it is. We have all done this, overfitting, underfitting, good fit, and you can see at the bottom part, very relatable. Underfitting is where you are hardly able to represent the patterns properly. For regression, you can see the data points are like this, but the model is just like this, just a linear straight line. That is an underfit model. An overfit model on the extreme left-hand side is somewhat like this. That's an overfit model. Overfit model is where you're able to perfectly represent all the patterns well. That is an overfit model. And the good fit model is somewhere in the middle. That's a good fit model. Right? So underfit model is extreme right-hand side, not at all able to represent the data points. Overfit model is on the extreme left-hand side. You're able to perfectly represent all the data points. And good fit model is coming somewhere in the middle, where you're able to just about learn the patterns. Okay, okay. That is how we look at a good fit model, reasonably good fit model. Okay. Talking about a classification problem, again, we have underfit, we have overfit, we have good fit. Underfit models are those models where, again, you're not able to learn the patterns well. We have blue classes, we have orange classes, and This is that separating surface, and you can see the separation is we are unable to learn the perfect separation between blues and oranges. We are unable to find the ideal separation between the blue and the orange class. This is an underfit model. Underfit means you are not able to learn the patterns well. You have learned nothing out of it actually. Overfit model is where you have learned the patterns too well. On the training data, we have found the separation between the blue and the orange really well. That is an overfit model. And finally, the good fit model is where we have just about okay found the separation. That's a good fit model. That's the inference we are able to get. So this is how we understand the difference between regression and classification actually, intuitively. Regression is best fit, classification is best separation. Now to take back to the conversation, go back to the original conversation that we were having. How does this kind of a pair plot help you in the context of a classification problem? If you look at this, the diagonals will tell you how good a particular feature is in terms of how the classes are separated. So you can actually look at the class separation and you can try to understand how well the classes are separated. So here you've got, let's say the plasma feature. I'm particularly highlighting the plasma feature right now, and you can clearly see specifically with respect to the plasma feature, we have the blue class and we have the orange class, right? All of you are able to see the plasma feature. We have the blue class and we have the orange class. Blue class corresponds to person not diabetic, 0 class, and orange class corresponds to 1 person is diabetic. So we have two classes, blue class and orange class. One is person not diabetic, one is person diabetic. That is what we are able to see. So plasma is nothing but the glucose level. What is the glucose level in the bloodstream? That is the plasma. Again, I repeat, plasma stands for the glucose level. What is the overall glucose level in the bloodstream? That's what we refer to as the plasma. Okay, and we can clearly see that plasma is a very good predictor of diabetes status. So we can say that more the plasma, the person is more prone to diabetes, and lesser the plasma, the person is less prone to diabetes. Okay, so if the amount of glucose in the bloodstream is more, I mean, you can just take a look at this pair plot again and see, like you'll be able to observe that typically the average, this is like 1 and this is like 0. You can clearly see the y-axis is nothing but frequency. It's a histogram, smooth histogram, KDE, right? This is like your plasma. Plasma is nothing but blood glucose. So we can clearly say that the average glucose level for diabetic people is much higher, and the average glucose level for non-diabetic people is much lower. So that means uh, another way to twist this will be, okay, we can say that if I know the glucose level in the bloodstream, okay, if I know the glucose level in the person's bloodstream, I can very accurately find out whether the person is suffering from diabetes or not. Okay, so once again, if I know the glucose level in the bloodstream, I can predict very accurately whether the person is suffering from diabetes or not. Okay, so depending on the glucose level, we can accurately predict diabetes status. If the glucose level is more, the person is more prone to diabetes, and if the glucose level is less, the person is less prone to diabetes. So again, I repeat, if the glucose level is more, the person is more prone to diabetes, and if the glucose level is less, then the person is less prone to diabetes. So the glucose is a very good predictor of, in a way, of diabetes status. Okay, so the glucose level in the bloodstream is a very good predictor of diabetes. That's the inference we can get. Okay, so the amount of glucose you have is a very good estimator, a very good predictor of diabetes status. That's the way to look at it overall. So this is how we can basically use a pair plot for feature selection, right? So, and on the contrary, if you look at the bottom one, so the better the separation between the classes, the better the quality of the feature. In fact, that is what we are doing in classification, right? In classification, we are trying to find the class separation. On the contrary, the next feature, blood pressure, is actually not a good quality feature. Blood pressure is not a good feature because you can see that no matter uh, if the blood pressure is high, also the person is equally likely to be diabetic or not diabetic. So blood pressure per se is not an important indicator of whether a person is diabetic or not diabetic. That is what we are able to get from the blood pressure feature. Okay, so a lot of overlaps we are able to see with respect to blood pressure. Okay, so you can clearly see that if the person's blood, if the person's blood pressure is high, they may be diabetic, may not be diabetic. If the person's blood pressure is low, again they may be diabetic, may not be diabetic. So we can again very clearly see that blood pressure is a very important indicator of diabetes. That's the inference we can get right now. So blood pressure is again a very important indicator of the overall diabetes status. Diabetes, not a very important indicator of diabetes status. So if the features are Overlapping, it is not a good feature. If the classes are overlapping, the feature is not good. If the classes are highly separated, then the feature is actually good. That's the inference we can, we can once again get from this and draw from this overall. Okay, I hope this is absolutely clear. People are clear. People are sorted correct. Now the problem
Uh,
is that this is something we cannot do manually. Like here,
uh,
obviously, we can just see the picture and say, okay, this is a good feature. You can say this is not a good feature, but we need a mathematical way to do it, right? We
mhm.
won't be visually seeing this, and pair plot is the starting point, definitely, but we want a more mathematical approach, and this is where inferential stat actually comes in. Okay, so what we do
Yes.
here is, so this is the same data set. Let me just take you back to the notebook once again. So we have seen the pair plot, and what we do is we create two classes. Look at it. Look at the code here. Demo class double equal to one plasma. So what does this mean? This will consist of the plasma values for all your diabetic people.
Mm.
So we are calling it plasma diabetic. So this will consist of all the plasma values of the diabetic people. So and this will consist of all the plasma values of the non-diabetic people. So we are simply creating two arrays, or rather two panda series. Two arrays, two lists we are creating. Think of it. To be more clear, it's a panda series. So this plasma column consists of the entire data across all the patients, right? So this plasma column consisted of all the values across all the patients. Across all the patients, it consists of all the values, right?
Yes,
Is it
sir.
clear? That is what it consisted of. That's the plasma feature. It consisted of the values across all the patients. That is what it had. And what you see here, what you see here right now. So the first one, the plasma column consisted of all the values across all the patients. This column consists of the plasma values only for the diabetic people, and the next one consists of the plasma values for all the non-diabetic people. Okay, so
Ye-
this one consists of all the plasma values for the diabetic people, and this one consists of all the plasma values for the non-diabetic people. So that's the inference we are able to, kind of able to get from it.
mm.
So we have created two separate arrays right now. One is the plasma values for diabetic people, and two is the plasma values for a set of non-diabetic people. And if I just visualize this thing, this is the same thing it will look like. So this visualization and this visualization are one and the same thing. So this one and this one are the same thing. So we just created two arrays in the process. Is it clear? Until now, you're fine. Prashant,
Yes,
this
sir.
makes sense,
Fine
right?
for me.
These are two different arrays I've got. So one is array of plasma diabetic people, and one is an array of plasma non-diabetic people. Now
Non-diabetic.
what I want to do, these are like two samples, and now we will go do like something like a two sample t-test. So think of this as sample one, your orange as sample one, and think of your blue as sample two. Now what I want to do is I want to basically compare the means across both the samples. This is like your sample one, this is like your sample two, and I want to basically compare the population means for sample one and sample two. So we are trying to find out how separate the means are, because that's what we are primarily trying to do in a classification problem, right, Prashant?
Yes, sir.
Classification, we are ultimately trying to find the class separation. We're trying to figure out, okay, do I see a significant difference between the classes with respect to the plasma feature in the population? Sample, this is the sample data. So based on the sample data, I want to infer in the population, is there a significant difference between the classes? Do I see a significant separation between the classes in the population?
Mm.
That is the thing that we are, kind of primarily trying to do here. So do I see a significant difference between the classes in the population? That's
Got
the
it,
that's
sir.
the idea, right? So if you think from the hypothesis testing perspective, so you don't have to do this manually. The code is just one line. So all that we do is so now that I have the two arrays, all that I do, we do a Will Shapiro test. Have you heard of these things? Shapiro test,
Yes, sir.
normality test. So we have to ensure that the distributions are normal, right? So we do a Shapiro test to check the normality. Okay, these are
Mm.
the two arrays we have got, and then we will do a two sample t-test. This is the two sample t-test we are doing, independent t-test. Stat dot t-test ind, class diabetic, this is the array one, and class non-diabetic array two. Sample one, sample two, feed it into the t-test ind function. This you have also used, right, Prashant?
Yes,
And you are
sir.
able to see a p-value which is coming out to be 10 by 143. Now,
Mm.
obviously, we know that lower the p-value, the more significant the feature. Now, if I have to be a little bit more, you know, intuitive here, You can think of the null hypothesis and alternate hypothesis. How will they look like? Specifically with respect to a two sample independent t-test, how will the null and alternate look like? So the null hypothesis will be that the mean for the mean for diabetes and the mean for non-diabetes are equal. That is, and alternate hypothesis will be something like this, not equal. Again, this is something that is not manually done. You don't have to worry about the hypothesis conditions here because we will not be creating a hypothesis test manually. The t-test IND function is already defined. Everything is defined. So you simply have to use the function, apply it. This is not like those traditional problems that you have probably seen where you will have to find out the hypothesis conditions yourself and frame it. No. But this is how it will look like. Okay, you've got sample one, you've got sample two. You frame the hypothesis conditions. What is H naught? What is HA? You frame it. And HA is what you are trying to prove. So what you are trying to prove here is that, okay, the mean for the diabetic class is significantly different from the mean for the non-diabetic class. That's the way how we look at it. Okay, so the mean for the diabetic class is significantly different from the mean for the not diabetic class. That's the way how we look at it. So the mean for diabetic class is again significantly different from the mean for the not diabetic class. So we are able to see a very significant separation between the means here. Okay, so that is what we are actually trying to prove. So we are trying to prove the alternate hypothesis. So alternate hypothesis is what we are ultimately trying to once again prove. Okay, and since the p-value comes out to be very low, we know if the p is less than 5% or lower the p-value, the more you reject null, isn't it? So if the p-value is very, 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 very small, you will reject null more. You'll accept alternate. So alternate is proven. And typically in inferential stats, 5% is just a baseline number that we have generally seen. But what we do is we always do a comparative analysis. We always say that, okay, lower the p-value, the more, the better the quality of the feature actually. I have to just write it down. So let's put it this way. We can say that lower the p-value. The condition we have generally seen is that, okay, if the p-value is less than, you reject null. We can further say lower the p-value, the more we reject null. The lower the p-value, the more we reject null. The lower the p-value, the more we reject null. And the more we reject null, we can say the more the separation. Lower the p-value, the more we reject null. And the more we reject null, what we can say, the more we reject null, we can say the more the class separation. More the class separation. More we reject null, the more the class separation, the more the separation between the diabetes and the non-diabetic class. That is what we are able to see right now. That's the inference we are
generally
able to see.
the null
So
hypothesis
generally
is
speaking,
like
the lower the p-value, the more we reject null, the more the class separation, and better the feature. So
okay.
to convey this from a feature selection perspective, we will basically do a two sample independent t-test with respect to all the features. Okay, so do a two sample independent t-test with respect to all the features. Compare the p-values. If the p-value is very small, that means it's a good feature. If the p-value is very large, it is not a good feature. Now, two sample
Okay.
independent t-test with respect to two classes. If there are two classes, then you do a two sample test, right? If there are more than two classes, then we do an ANOVA test. The code for ANOVA looks somewhat like this, F1 way. This code also you have seen probably.
Yes, sir.
This is when you've got more than two classes. Let's say we've got type 1, type 2, type 3 diabetes, something like that. So we've got three classes, and now again the idea is the same. See, this code will work for two classes also, right? Answers are the same. Even if there are two classes, the answers are the same. But if there are more than two classes, if there is mu1, mu2, and mu3, then you have to use F1 way function. You'll say class 1, class 2, class 3, and you'll get a p-value. Again, lower the p-value, better the quality of the feature. So this is how we actually use it. Now, obviously, in a real world scenario, we won't be using this like t-test IND manually. So what we do, we go and, okay, by the way, you can see the same thing for blood pressure. I've done the same analysis for blood pressure. You can see this is BP. So this is pressure for diabetic people and pressure for non-diabetic people. Same way we are looking at this distribution. And I told you visually this is not a good feature. Let us say statistically, what is it conveying? Statistically, when I do a two sample independent t-test for the blood pressure feature, I get 0.07. And you see, it is basically 7.15%. What does this mean?
Mm.
7.15. That means 7.15 is more than 5%. It's much, much higher. So this is not a good quality feature. So
Mm.
plasma was a good quality feature. It was 10 to the power minus 53. E minus 43 means 10 power minus 43. It was a good quality feature. This is not a good quality feature. So just by doing an independent t-test, I know how we can get. What's a better way to do it? You don't have to manually like create these arrays and do this. This is again like a very process. So the manual way to do it, a simple automated way of doing it is this. This is a practical way we do feature selection using p-values. Okay? Two lines of code. You automatically get the p-values for all the features. Okay, and you can just
Okay.
see the bottom part. We get this. This is that a 10 per minus 43 that we got,
Mm.
and see this. This is
Mm.
that 7.15 that we got.
Mm.
E minus 02 means 10 per minus 2. That means it is like 0.07. The same 0.07. Okay,
Mm.
same numbers we are getting. If
Sir,
you have
can
a
you
data
share
set with
that piece
50
of
odd
code
features,
in the chat,
I
sir?
will do that. Yes, I'll do that. Yes, if you have a data set where you've got 50 odd features, and if you run this piece of code, so what we do is right up front we do a pair plot, and we run this piece of code. We find out what are the p values across all the features. And if your p value is very small, that means it is a good feature. If your p value is very large, it is not a good feature, overlapping feature. So we will try to drop those kinds of features. Okay, this is one of the approaches that is used. Now, having said that, let me clarify: p values are still a very less used technique. P values, although this is one of the ways to do it, and also interviews and all, if you're asked questions, at least you have something to answer. But a slightly better approach would be, I would say, a slightly better approach would be to go ahead and kind of use feature importances. We've all seen decision trees, random forest feature importances, right? That's a better way to do it. Instead of using p-values, use feature importances, which is a much more robust way of doing feature selection. Because that's a model-based technique. This is a non-model-based technique. This is a parametric technique. So you're not actually building any model. You're statistically looking at your data and trying to infer. Could this be a good feature? Could this not be a good feature? That is all that you're doing. This is a non-statistical technique, actually. Data is loaded in, and let me go ahead and do the rest of the stuff. So this is just another some really cool things in Collab where you can click on these recommended plots and all that, and automatically it will analyze your data and do some automated plotting. Very similar to like Suiteways yesterday. We are seeing a lot of these things coming up in today's tools. So it will automatically generate different types of charts for you. Anyways, let me run this. This is the manual way we did the statistic stuff. All of you can see the screen. And right at the very end, what I showed you was how we can get all the p-values for the whole data set in one go. And the way to work this out would be to go ahead and uh, you know say that, hey, so p-value is the smaller the p-value, the better the quality of the feature, right? So I repeat again, the smaller the p-value, the better the quality of the feature, and the higher the p-value, the worse the feature. That's the inference we can get out of it. That's what we can do. All right. Now, what about the decision tree part I was talking about? It. I think that from here it is very clearly evident that so we have the data set which is demo, right? So let me just go and say demo.columns for a minute. And this is a better way to see it. So if you want to investigate the whole thing together, the best way to do it is to kind of maybe create a table. So I've got this is the list of columns we have. Okay, so we have a list of columns in demo, and we also have uh, the p-values. So you can correspond the p-values to the respective columns. So we know that, okay, this is the p-value for the glucose feature, and this is the p-value for the corresponding blood pressure feature. We're able to see the p-values for the respective features. We can clearly see this is a better quality. But what's the other way to do it? The other way to do it was, as I said, we can use feature importance. And feature importance is a very simple idea. So what we do here is we create a tree-based model, and we can, I think the best way to do it is an ensemble. So maybe we can do something like a random forest classifier to create a tree-based model. Once again, this is the random forest classifier that I will create. And don't give any hyperparameters. Do not add any hyperparameters like depth and all those kinds of things. Don't add any hyperparameters per se. So that is another important thing to keep in mind. And what you do is you do an rf.pick on x comma y. Okay, so we have done the x comma y already here. So have we? Okay, yes, we have got that. So x is nothing but the features, y is nothing but the class, and you do a simple random forest classifier on x comma y. That's it. And once you train the model, the final step that you want to add is you want to show the feature importance values. You say rf dot feature uh, underscore importances underscore. And once you do that, the tree-based model or the random forest will be created, and automatically you will get to see that what are the feature importance values against the respective features. Now, again, there is an entire mathematics around how these numbers are getting generated. I will not get to that, but this is based on information gain and entropy. Very clearly, from this feature importance based technique, again, the most important feature is indeed glucose or blood pressure. Sorry, glucose, plasma, that feature. Blood pressure is actually having a lower feature importance. So it is not like whether I should use this technique or that technique. Ultimately, if a feature is a good quality feature, both the techniques will, narrow down to the same answers. Get the same answers irrespective of what technique you use. So, which whether you use the feature importance technique or you go and use the other technique. So both the techniques will, by and large, give you the same answers. Feature importance, you can work for binary as well as multi-class problems. So build a tree-based model. This is a model-based technique. A model is built, and now on the basis of that, we are saying that okay, which feature is important based on where it is chosen on the tree. Typically, features at the top of the tree are more important. At the root node or around that root node, top of the tree are more important features because they are getting selected because they are important. They are reducing entropy a lot. They are creating the separations as well. And features uh, towards the bottom of the tree, or features that are not getting selected in the decision tree, they are less important features.
And this is the one most used, sir.
Yeah, this is a much better approach because we are building a model and it's more robust. But by and large, if, as I said, to start my initial thing, what I mentioned, if you have a good quality feature, p-value based technique, this technique, they will give the same answers by and large. And this is again a concrete data set. It's a very simple data set. It's not a very real world case study, but it is again just to recap the concepts basically. So what kind of data do we have here? We have the different attributes of concrete like cement, slag, ash, water, superplastic, coarse aggregate, fine aggregate, age. So we have the different attributes of concrete, and based on the different attributes of concrete, we are trying to predict the strength of concrete. So strength actually stands for CSMPA. So CSMPA basically stands for concrete strength million Pascal. So so we are looking at the different features of concrete, and based on the different features of concrete, we are trying to predict what is the strength of concrete. That makes it a regression problem. So all of you can take a look at this one. This is the data set, the solutioning that I have shared with all of you, and pretty much in line with what you have done. But there are a few other new ideas that I wanted to propose to all of you, which are a little bit different from what you have seen. So again, this is my data set: cement, slag, fly ash, water, superplastic, coarse aggregate, fine aggregate, age. So we have the different features of a typical concrete mixture, and based on this, we are trying to predict the strength. Right. So once again, it's the concrete strength prediction problem that we are doing. So the output that we are trying to estimate right now is the strength. Strength is what we are trying to predict. So once again, you can look at the pair plot of your original data, and you can very clearly see that my data is seemingly highly skewed. So a lot of right skew, a lot of left skew, we are able to see in the original data, and this is the inference we are able to get. Right. So iteration one, what this is again the original correlation matrix that we are able to see. We can clearly see all the 8 input features, and the output CSMPA is what we are able to observe. Okay, so we have the 8 input features, and the output CSMPA is the concrete strength that we are able to observe right now. Okay, so concrete strength is again, something that we are trying to predict right now. So we are trying to find out which of the features are the best predictors of concrete strength. So strength prediction is what we are ultimately trying to do here. We can clearly see that cement is the best predictor of strength, followed by superplastic, and that is followed by age. Okay, so this is just a very basic analysis that you're doing. Obviously, right at the outset, you're able to see that none of the features are good quality features. All the features are seemingly very poor quality features. So the solution here is to basically combine all the features and build like a single model. Maybe individually the features are not contributing much, but when you probably combine the features into one entity, then you will end up getting a better quality thing. That's the inference that you will probably find here. Okay. Moving on, friends, we can come all the way down. This is again some auto EDL libraries. I showed you SweetWiz already before, so you can take a look at that. This is the baseline model, as you rightly mentioned, train test split, and we are applying linear regression on the original data, and we're getting something close to 60%. So the numbers might be different based on your, test size and your random state. The numbers can vary a little, but broadly, this is what we are getting. So we have a test R squared or a test accuracy that is coming out to be something around 62% or inference that we are 60%, not 62, 60% R squared is what we are approximately getting right now. That is what we are able to see. Okay. Now moving on, we are able to see the uh, we're able to see the power transform right now. I'll just quickly show you the power transformation step. This is the way to do it, right? So this is the linear regression after doing power transform, and you can clearly see the two-step process. The first we transform the data. Transform means pt.fit transform is what we do. The first we transform the data, and then we do linear regression. Okay, so once again, first step we transform the data, and next step we do linear regression. So step one, we will transform the data. So whatever data we have, we will do pt.fit transform and explain we will do, and we create the transformed train data, and then we also transform the text based on the learnings. This is again the first step we do power transform, and the next step we go back and do linear regression. That is how we once again proceed. Okay. So first step power transform, and the next step once again uh, we are doing linear regression. That's the idea. Okay, perfect. Now moving on, what we will do now is we'll go back and seeing the model. We're getting around 79% output approximately, and definitely this is a better model than we had. And I wanted to clarify this clearly that whenever you are analyzing models, whenever you are comparing models, it is very important to look at both the models together simultaneously. Don't just look at one model, but it's important to look at both the models together. It is important to look at both the models simultaneously and compare which one is better. Okay, so here you're looking at uh, linear regression, the baseline linear regression model. You're seeing what is the accuracy, and after doing power transformer, you're once again doing linear regression and trying to find out the accuracy, and you're comparing the results based on that. That's the way how we are kind of driving this. Okay, so you're able to clearly see that we have a better model after doing power transform. Now, what I wanted to show here is the new part is basically this. This is what I wanted to show you. I've actually used something called a pipeline, right? So look at this code snippet, all of you. This is again something little different from what you're probably seeing in the classes. So this is the first piece of code is the one where I'm actually using the normal power transform. Okay, so you do a train test plate and you do a fit transform. So this is the manual way how we have generally done things, right? And then after you transform the data, you can do a linear regression. Now, what we are seeing here is more like a kind of a pipeline. Pipeline is a very specific workflow that we are creating where I'm actually defining a series of steps. This is equivalent to this code. You can see the answers are also exactly same, 79.97%. And test accuracy 79.97%. Exactly the same accuracies I'm getting right now. And if you take a look at the code, what's going on, I've instantiated a pipeline. What is a pipeline exactly? A pipeline is a series of different steps. Okay, so a pipeline is a sequence of different steps. So, so there are different steps that we have in the pipeline right now. So step one, step two, step three, step four, step five, and so on. So these are all the different steps that we have in the pipeline. That is what we call a pipeline here. So that's the inference. So what we did here, once again, we instantiated the pipeline, and this pipeline consisted of two steps. So once again, there are two steps in the pipeline. First, you've got the code again looks somewhat like this. You've got a step name. It can be any variable name. You can give it a name of a variable step name and a step class. And once again, there is a step name, which is LR, and a step class, which is linear regression. Okay, so we have a pipeline, and the pipeline consists of two steps. So there are two steps in the pipeline. One is the step name, and one is the step class. The step name is the variable name, and step class is what that step is all about. Second, again, we have a step name, and then we have a step class, what that step is all about. Okay, so this is how we have instantiated the whole pipeline, and we are wrapping it around the variable. And then what are we doing? We are saying pipe.fit transfer, pitch, extend, comma, white train. This is how we are doing this. Okay, so once again, we instantiate the whole pipeline. We define the two steps, power transform and linear regression. These are the two steps that we define in the pipeline. So first we have power transform. Next we have linear regression. And then what we do is we go and encapsulate those steps in the pipe variable. And then we go back and fit the pipeline on the training data. So we go and fit the pipeline in the training data, which is explained from a white train. That's the way how we go and do this. So this is the explain white train that we have done. That's the inference that we are getting through. So two-step process. First, you fit the model on the training data, and then we go and do the scoring, and we calculate the accuracies on the unseen text data. Okay, so we fit the model on the training data, and we go and calculate the accuracies on the unseen text data. Okay. Uh, this is cross validation we have done. All of you know that cross val scores are taking the average cross validation score, and very clearly this is the better model. Now, how is it beneficial compared to the previous one? Well, we don't have to manually do fit transform anymore. And usually a machine learning pipeline consists of multiple steps. Like when you're building a model, it's not just the algorithm that you're using, but there are multiple pre-processing steps. You might be doing power transform, standard scaler, one-hot encoder. All of these things can be part of the pipeline. The pipeline can help in like it basically helps in modularizing the code better. You can create a module, you can segment the code better, and you can most importantly, you can modularize the code. This is like a module, and this pipe can be used anywhere else, which is what I've done. Next time I'm calling it, I'm just saying pipe.fit. So when I say pipe.fit, first it will do the transform, then it will do the linear regression.fit. Automatically, the steps in the pipeline will be executed. And then there are more complex workflows you can create. You can create pipelines for different steps in the process, and then you can basically create a pipeline of pipelines. That's the way how we can go back and write this. Actually, here is a decision tree classifier regressor once again. I've once again put this in a pipeline. No pre-processing step, just the algorithm itself. And we can again see that the model is slightly better. Test output is 87% approximately. And if you come all the way down, scroll all the way down, I've used PCA also as an example. Power transform, PCA, then linear regression. See how pipelines help. I can wrap all these steps together in one piece. And if you come all the way down, here goes the gradient boosting regression. So once I use gradient boosting, I'm just instantiating and setting an estimators of 1500. I'm getting 94% test accuracy. An average cross validation accuracy is coming out to be 92%. You can see this is a much better model compared to what I had before. Okay, and of course, something I mentioned yesterday, you can of course go back and create a kind of a validation curve. It looks pretty beautiful right now, and this is again useful for hyperparameter tuning. You can plot your, you can plot your depth along the x-axis, and you can plot your scores along the y-axis. So x-axis we have the depth, y-axis we have the score, and we can easily go back and see that as the depth is very low, the training and testing scores are very low. The model is highly underfit. And as the depth increases, the model becomes more and more overfit. Okay. That's the inference we are able to get. So we can clearly see how depth is impacting the performance of the model. And if you come down, we have got a validation curve for random forest regress. This is the validation curve for random forest regress. X-axis we have an estimator, and y-axis we have the accuracy or the R squared of the model. It's a regression problem, right? And we can again clearly see that as the number of estimators are less, the model is underfit, which is expected. If I have very less number of trees in the forest, then it's a very basic model, underfit model. And as the number of trees increases, as we increase the number of trees, as the number of trees increases, what will happen? We are able to see that it becomes a more and more good fit model. The training and validation both are going up. It's becoming more good fit. And after a point, it will probably tend to overfitting zone. So beyond the point, as the estimators increases further, the training will kind of stagnate and the testing will kind of come down. So we will get a more of an overfit model. That's the inference we will end up getting generally. That is what we get. And and the best part about pipelines is also it can be used for hyperparameter tuning. I think this is like really cool. So we can absolutely use the pipelines from the perspective of hyperparameter tuning with the CV. I just used a small kind of an example here. You can see now the normal hyperparameter tuning that you have seen is you can only use bits per CV on a single algorithm. Let's say you're using something like like a gradient boosting regressor kind of thing. So that is generally what we have what we have seen so far. You've seen like a gradient boosting regressor, an estimator you can tune. That's the typical hyperparameter tuning that we have seen, friends, right? Now, what I'm talking about here is you can tune several hyperparameters across several steps. It is not just gradient boosting, but see how I can define a pipeline with all these steps in between: standard scalar, poly features, power transform, PCA, gradient boosting, regressor. And each of these steps will have hyperparameters present within them. So poly features will have degree, PCA will have n components, and gradient boosting will have n estimators. And these are the hyperparameters that we will ultimately want to tune. Okay, so we'll basically want to figure out what is the value of the hyperparameters here. Okay, so this is the range of hyperparameters we'll try to tune. So degree can be either 2 or 3, n components either 30 or 40, n estimators either 10, 20, 30, 40, 50. So, and now we can tune it. So all these hyperparameters together will be tuned. And then finally, at the end of it all, the code is the same. You can see it is the same code: best params, best score, the same grid search CP code that you have seen. And at the very end, we will actually get to see the best parameter values that will be available here. We can observe that. So you're able to see this, everybody. All right, perfect, perfect. We hope you're able to understand this. Yeah. So this is the ideal parameter values that you're able to see. Best parameter values. Okay. All right, this is pretty much what it is. I think the solutioning was actually quite straightforward, and now what I wanted to show you were a few other different ideas, and this is where I've also done a comparative analysis of algorithms. So first, we did a linear regression, and right to the extreme right, we've got an gradient boosting regressor. You can actually kind of plot it out in a plot as well. How do you compare multiple algorithms? So the key takeaways from this exercise: one was um, the aspect of pipelines we saw, how we are able to build a better quality model with Power Transform, and how pipelines can you can add multiple steps in a pipeline, and how can you do hyperparameter tuning across multiple steps using a pipeline. We also were able to see the validation curve part, like what we saw yesterday, especially if you have to fine tune the parameters. How do validation curves really help? So one is this Costa Rican household data set that we are taking right now. And what we are trying to do is we are looking at the different attributes of a particular household, and based on that we are trying to predict the poverty level of the household. And I think from a social aspect, this is a very interesting use case also. I think very interesting use case, I would say, purely from a from a very social context as well. So what we are once again trying to do is looking at the different features of a household. We are trying to predict what is the poverty level of the household per se. So is it a rich household or is it a poor household? That's what we are in a way trying to predict. So one of the other ways of doing it is you can do a manual survey. You can do a census survey. You can ask people about their income status. That's one way to do it. But people may not always be very forthcoming and give the right answers. They will not disclose their incomes because everybody wants to save taxes, right? But then what we are proposing here is a very kind of a very objective approach where you're able to. So it's a very objective approach where we are trying to understand how rich or how poor the household is based on their observable attributes. So based on all the observable attributes of the household, we are trying to predict whether the household is rich or the household is poor. So that is the problem that we are specifically trying to solve here. That's what it is. Okay. So I hope this is clear. I hope the idea is absolutely clear to all of you. What we are, what is the problem that we are specifically trying to solve here. And if you look at your data set, very interesting data set, we are looking at real features of the household. So these are all the different features of the household that we have. So we are tracking how many females are there, how many males are there, what is the size of the household. We are tracking, is there a water provision, is there electricity, is the toilet connected, what is the main source of energy, uh, quality of the walls, quality of the roof. All of these are the features of the household that we have. Does it have a TV? So these are all the observable features. Somebody will visit the household and they will observe that, oh, these are the features of the household that we have. And based on that, we are trying to figure out what is the poverty status. Is it a rich household or is it a poor household? If you just come all the way down, this is the output column that we have. Now, why am I taking up this exercise? What are we? What is the takeaway from this problem statement? What are we trying to achieve? Well, what I wanted to show you here is how do you handle the classes? Like, let's say from a business perspective, does it make sense to have four different outputs here. So here we have extreme poverty, moderate poverty, vulnerable household, non-vulnerable household. These are the four different classes of outputs that we have right now. But if you ask me purely from a business perspective, if I if I have to answer this question purely from a business perspective, does it make sense to have four outputs? That's the question. Does it make sense to have four outputs right now? No, it doesn't. It does not make sense to have four outputs right now. We don't need four outputs. We just need to know whether the household is rich or poor. We do not need to understand what level of poverty the households are suffering from. Is it extreme poverty? Is it moderate poverty? Is it vulnerable household, non-vulnerable household? That is not needed. That's not needed to. We just need to know: is it a rich household or is it a poor household? So these are the four different categories of income that we are trying to. So based on the features of the household, we don't really need these because even if you end up building a classification model, even if you end up building a classification model, what will happen, friends? You will have a lot of overlap happening between class one and class two because whatever models that you end up building will be very likely confused between class one and class two. So model predicted extreme, but actually is moderate, or vice versa. Model predicted moderate, but actually is vulnerable. So a lot of those kinds of challenges will happen. The model predicted vulnerable, but actually so between one, two, three, lot of overlaps will happen. And even if you do the confusion matrix, you will see that the model will get very confused. Even if you do this, the model will end up being very confused. So to prevent that, what do? We go back and combine classes 1, 2, 3 and call it 4, and we combine classes 4 and call it rich. That's the inference. That's the way how we go back and do this whole thing. That's the idea. That's the basic way how we are doing this. I hope the concept is absolutely clear. So next time when you're working on any classification problem, always look for a way to reduce the number of classes. Don't try to have too many classes. So your first and foremost objective should be to build models where the number of classes are less. Okay, so always try to build models where the number of classes are less. Don't try to have too many classes. So try to build models where the number of classes are less because they will be more accurate. Then based on the business requirement, you can say, okay, let's take it back to 5 classes, 6 classes, 7 classes, so on and so forth. But iteration one, you should always try to build models where the number of classes are as less as possible. That's the first and foremost thing we should try to do. Okay. There is one more exercise I would like to clarify, share with all of you. This is again more of a general discussion once again, but this is also a very beautiful real world use case of regression. This is from the Mercedes Greener Manufacturing Competition. This was a live competition that Mercedes conducted back in 2017, and there was prize money that they announced also. A very interesting problem statement, and whatever you're seeing is not just in the context of Mercedes. You can actually extend this use case for several other avenues also. This is like a amount of time it takes to test a car. So Mercedes cars are highly customizable. Next time you want to order a Mercedes car, you can basically go to the application. You can choose what kind of features you want in the car. Highly customizable cars. You can choose the exact permutation combination of features that you want, and based on that, the car of your dreams will be kind of fitted out, right? So that's the idea. Right? So once again, we so we will look at all the different features of the car, and based on all the different features of the car, we will try to predict what is the time it takes to test the car. That is the idea. So here also we will look at the different features of the car, and based on the different features of the car, we will try to predict the amount of time it takes to test the car. It is uh, a time a car time prediction problem that we are trying to solve. That's the idea. Okay. And how is it helpful? Because you can give a correct ETA to the customers. If you know how much of time it will take to test the car, then the right kind of ETA can be given to the customer. You can give a right kind of estimated time of arrival. The right ETA can be given to the customers in terms of how much time it actually takes to test the car. So as I said, the right ETA can be given if you're able to accurately estimate how much time it takes to test the car, right? So customers will also know, okay, I will get my car delivered in so and so time. So interesting use case. Now, what I wanted to clarify through this example are a couple of ideas. Okay, let me take you to the Jupyter notebook. Just a small discussion. So rest, you can go to Kaggle, and oftentimes in all these competitions, people also share the code. You can go to the code section and you can sort by most votes. This is what I like to do, and then you can actually go and see some of these most voted kernels. So I simply opened up this one. This is by this fellow, Sudai Rajkumar, and you can just go on and open up this notebook. I've downloaded this one and opened this one up, and it's just a great way to see how other people have solved the problem. Anyways, coming back to the problem statement, this is actually the data set. It's a huge data set, very, very interesting data set. In case you want to later on analyze it, you can do that. It's also an excellent data set that is ideal for feature selection. You can already start to see there are 386 features of the car that we have. How many features we have in the car? We have overall 386 features in the car. Yeah, Shweta, you want to say something? Hello. So there are 386 features in the car, and based on that, we are trying to predict. We are effectively trying to predict how much of time it takes to test the car. This is the output Y that we are trying to predict. Now, if you look at the distribution plot for the output Y column, this is how the distribution plot looks like. Take a look at this. Very interesting. This is the output column. And what I am doing is, I am looking at the distribution plot for the output column. I'm trying to analyze the distribution of the output column. This is the distribution plot that we are doing for the output column. This is what we are able to see. You can clearly observe that most of the cars take average to less time to test, and few cars are taking a tremendous amount of time to test. Okay, I repeat again. Most cars are taking average to less time to test. So most of the cars that you have, they are taking average to less time to test. So most cars are taking average to less time to test, and few cars are taking a lot of time to test. That is the story right now. There are some cars that are taking a tremendous amount of time to test, and most cars are taking average to less amount of time to test. So this is a right skewed or a kind of a positively skewed distribution that you're able to see. That's the inference that you're able to get right. The second thing that you're able to understand is the peaks or the clusters. You can very clearly see that our data is divided into three groups or three clusters. This is the other inference that we're able to make out. This is cluster 1, cluster 2, and this is cluster 3. So we can very clearly see that our data is divided into three clusters or three groups. So we have group 1, group 2, and group 3. What do the three groups indicate? The three groups basically indicate different clusters of cars. So these are cars in cluster 1, which on an average have lesser testing time. These are all the cars in cluster 2, which on an average have middle testing time. Okay. And we have got cars in cluster 3, which on an average have around 110 units of testing time. So this is the overall amount of testing time we have got. Okay, so once again, uh, the whole data we have got right now, that will be whatever, 1,000 odd records or whatever number of observations we have the whole data. And we have managed to divide the data into three clusters or three groups, as we see. So we have cluster 1. Cluster 1 actually stands for a specific group of cars where the testing time is equal to around 80. Then we have cluster 2, which is a group of cars where the testing time is around 100. And we have cluster 3, which is again a specific group of cars where the testing time is around 120. So these are the three different groups or clusters of cars that we have right. Okay, so we have got three different groups or three different clusters of cars. Why is this thing important? Why is it important to know that there are three different groups or clusters of cars? So what you can now do is you can build a separate model for each and every cluster. This is how clustering is used in the larger supervised learning workflow. In case some of you are wondering, Sayan, how does it actually help us? All this is great, fine, but how does it help us? What do we do out of it? Well, what you can do now is you can build a separate model for each and every cluster. For cluster 1, you can build a separate supervised learning model. For cluster 2, you can build a separate supervised learning model. And for cluster 3, we can build a separate supervised learning model. We can build a separate model for each and every individual cluster. That's the way how we can run this. Okay, so 3 different clusters or 3 different groups of data we have right now, and we can build a separate model for each and every cluster. Now, generally what we have done is we have taken the whole data and we have built a single model just to write it down again. So based on X, we predicted Y. This is what we have done. So we have done the time prediction on the complete data. So we have taken the complete data, and taking the complete data into account, we have done the time prediction. We're trying to predict, okay, what is the time based on these factors. That's what we are trying to do. Okay, so based on this, what is the predicted time? That is what we are trying to do. Now what we will do, we will take the whole data, we will divide the data into 3, 4, 5 clusters. We take the complete data, we divide the data into 3 clusters, and each of these 3 clusters will denote 3 different groups of cars. These are cars in group 1, cars in group 2, cars in group 3. There are 3 different groups of cars we have, and the 3 different groups of cars demonstrate 3 different characteristics. And on each of these groups, we will build a separate model. On group 1 cars, we will build a separate supervised learning model. On group 2 cars, we will build a separate supervised learning model. And on group 3 cars, we will build a separate supervised learning model. So we will go and build a separate supervised learning model on each and every group and cluster of cars. So group 1, there is a separate model to predict the time. Group 2, there is a separate model to predict the time. And group 3, there is a separate model that we will build to predict the time. That's the way how we will go and run this. All right. And how is this approach helpful? Well, it will help you build a more accurate model. Okay, it will help you build a more accurate model. Instead of taking the whole data and building something, now you can build a more accurate model on the whole data. So it will help you build a more accurate model on the data. So you divide the data into different groups or clusters and build a single model for each and every cluster. It will be more accurate because now you're able to represent those specific patterns more accurately. So generally speaking, you will have a more accurate model by doing that. That's the idea. I hope it's clear. Everyone's able to understand the piece properly. I'll show you one more visualization in this to really help solidify the concept in your head. I think this particular diagram will also help you quite a bit. Let us see. Yeah, this one. It's a simple example of a housing price prediction. Now you can take a look at the data set right now, please. Look at the data set on the left hand side. Based on the size of the house, we are trying to predict what is the price of the house. So let's say that is the problem statement that we have, right? Okay, so based on the house size, we are trying to predict the house price. Okay, I repeat again, based on the house size, we are trying to predict what is the house price. That's what we are trying to do. Based on the size of the house, we are trying to predict what is the price of the house. That's the problem statement. X, based on X, we are trying to predict the Y. So we can represent the data in a two-dimensional scatter plot, size and price. And this is the whole visualization of our data. Now, one way to solve the problem is we can do regression. This is again doing regression on the whole data, right? So that's one way to solution this. Problem is that there are the patterns are very unique, right? So if you look at size versus price, there are lots of patterns in the data. I mean, there are different types of houses, friends, and for different houses, obviously, the dynamics of the pricing dynamics are very different for all the different groups and clusters of houses, right? So the pricing dynamics are very different for the different groups and clusters of houses. So what do we do? Instead of building one single model on the complete data, what we do is we do clustering first, like a k-means clustering we did yesterday, and we divide our data into 3 groups: small, medium, large, based on the size. Based on the size attribute, we try to divide the data into small houses, medium houses, large houses, 3 clusters of data. And even visually, you're able to make it out, right? So you can see that there is one kind of pattern here for small houses. There's some kind of pattern here for medium houses, mid-sized houses. And there is some kind of pattern here for large size houses. So we simply go and divide the data into three groups. And now we've separately built different regression models on these different groups. You can see very clearly for the small houses, the patterns are linear. For the mid-sized houses, the patterns are kind of like polynomial. And for the large houses, the patterns are logarithmic. This way, we will end up building a more accurate model. So, because you're able to represent the specific patterns in those specific groups more accurately. And this is also a very, very common approach that is used generally. And this is often referred to as semi-supervised learning, where we do unsupervised learning and then do supervised learning. So you do clustering. First, you do clustering, divide your data into different groups or clusters, and then each cluster becomes a workflow of its own. So for cluster one, we do supervised learning models separately. Cluster two, we do supervised learning separately, and cluster three, we do supervised learning separately. Oftentimes, people have a question that the sign, how many models do we really have then? Well, we actually have three models. We have model one, model two, and model three. All the three models are existing simultaneously in production. So when it comes to deployment, you will go and deploy all the three models. You will not deploy only model one or only model two, no. You will go and, in reality, you will deploy all the three models in production. And then what happens when we get new data? When new data comes, what will happen? When new data comes, first we will figure out what cluster that data belongs to. So whenever we get some new data, first we will figure out what cluster that data belongs to. Figure out what is the group or cluster that particular data set belongs to. And once you figure out the data set, the particular the data set where the cluster belongs to, sorry. First, you figure out what group that data belongs to, and then for that particular cluster, you apply that particular supervised learning model. So when we get new data in production, X new will come, K means dot predict will happen, find out the cluster label, and if it is cluster label 0, do this model 1 dot predict. If cluster label 1, do model 2 dot predict. Else if cluster level 2, do model 3 dot predict. So there's an else if else statement that you will apply. So whichever cluster my data belongs to, that particular supervised learning model dot predict. So this is the way you can define a workflow, and this is a very common approach. I mean, now that we are entering into the final phases of the session and of our DSE course in general, this is something I feel you should be aware of. In production, this is a very common approach. You will never build a single model. You will always analyze your data, identify how many groups or clusters are there in the data, and for separate groups, they will demonstrate different patterns. And for different groups of data, you will typically go back and build a different model. So first of all, how do machines handle text data? Let's take an example. Straight away take an example and understand this a little better. So let's say we have the text Hyderabad is the capital of Telangana, right? So on the left hand side, I'm feeding a text data to the machine. And let us say the complete text data that we have right now is Hyderabad is the capital of Telangana. That is the whole text data that we have right now. So what is the very first step when we are starting to work with text data? What is the very first step? The very first step is the machine tries to identify the tokens. What are the tokens that are coming out of this text? So the complete text data that we have is Hyderabad is the capital of Telangana. That is the whole text data that we have. And what we do is we go and take that complete text and we break that complete text data in the form of tokens. And what are the tokens we have in the process? Hyderabad is the capital of Telangana. These are the 6 tokens that we have in the process. Okay, so these are the 6 tokens that we go and have in the process. Hyderabad is the capital of Telangana. And these are the 6 specific tokens that we have. Tokens are the smallest individual unit of a text. What is a token exactly? A token is nothing but the smallest individual unit of a text. That is what a token actually is. Okay, so once again I repeat, what is a token? A token is a smallest individual unit of a text. That is what a token actually is in general. And here a token is a word. We are looking at a word token, but it can be anything else. It doesn't necessarily have to be a word token. It can be a word token or it can be something else. Okay, so just to clarify. So yeah, so token can be anything for that matter. It can be a word token or it can be some other kind of token we can also have. So here we specifically have a word token. That's the inference we are able to get. Now, So first step is tokenization. Tokenization again is the process where we take that complete text data. Okay, so tokenization is the process where we take the whole text data. This is what you're able to see. And from that text data, we go and break it into unique words. Now, what we do is the next step that we do is we do something called vectorization because we cannot give words and we cannot feed characters to a machine learning model. I think you know that machine learning models are based on algorithms, linear regression, logistic regression, decision trees, all of these kinds of things that we have talked about all through the sessions. Right? So we have talked about all these things, and then we cannot use the like the normal category character or words or characters or alphabets in this data. We cannot. We have to convert it into some kind of a numerical form, and only then we could use it. That's the idea. How do we do that? We do something called vectorization. Just to give a small example, how do we actually do this? Let's see. We are also introducing one more important term or jargon right now, which is called a document. So, what is a document? A document is basically one row or one observation. Okay. So, we are seeing one document, and the document is nothing but one row or one observation. And a document can be anything. A document can be one review. One document can be one Amazon review. It can be one Twitter tweet. It can be one Facebook post. So one document can be absolutely anything. So this is like one document, what you're able to see on the screen right now. Okay, so document one, he is a good boy, she is also good. Okay, I repeat again. Document one, he is a good boy, she is also good. Document two, Radhika is a good person. That is what we are able to see. So we are able to observe two documents right now. So document one, he is a good boy, she is also good. And document two, Radhika is a good person. These are the two documents that we are able to see right now. So the very first step that we do is we look across both the documents and we find out the list of unique words, which is called a vocabulary. So we look at document one and document two, and we find out what are the list of unique words that are present across both the documents. So if I see across document one and document two, both these documents, what are the list of unique words we are able to find? And that is what we call the vocabulary. So we construct a vocabulary. And this is the very first step that we do in an NLP problem. Now, right now, in this example, we are only having two documents, but in reality, there'll be several hundreds of documents you might have, hundreds to thousands of reviews of customer data you might be having in reality. So, as I said, the number can be in several hundreds of thousands or whatever. It will be a massive data set you'll be having. Okay, so yeah, so just as I said, you'll be you look at the documents and you will go back and go through all the documents and find out the list of unique words. How many unique words are present across the document, which is called a vocabulary. So we construct a vocabulary from the whole data. That is the first thing we do. Then what we do is we simply go and create what we call a document matrix or a DTM. Okay, we simply create a document matrix or a DTM, which looks somewhat like this. Very simple. So again, just to summarize, uh, review one, review two, which I'm calling as document one and document two. Go through both the documents, find out the list of unique words. What are the list of unique words that are present across both the documents? So find out the list of unique words that are present across the documents. And once that is done, once we are able to uh, find out the list of unique words, then we represent those words along the rows. Okay, so we represent all those words along the rows, and we represent the documents along the column. Sorry, we represent all those words along the columns, and we represent the document along the rows. And this is what how we create a document matrix or DTM. So we call it a DTM or what we refer to as a document matrix, so to say. That's the way how we create a DTM or a document matrix. Okay, so that's the way how we do this. I hope this is absolutely clear. The idea is clear. So you can see here, document one and document two are part of my rows, And along the columns, we have A also boy good, he is person, she Radhika. These are the list of unique words that we originally had. And the cells are showcasing the word counts. So we are seeing document one consists of this word this many times, and document two consists of this word this many times, and document three consists of this particular word this many times. So document one consists of the word person zero times, and document two consists of the word Radhika, let's say one time. So we are actually looking at the word counts in the process, how many times the word counts are occurring. That is what we are able to fundamentally track. And what we have achieved at a high level, what have we fundamentally achieved at a high level? Uh, we started with a completely unstructured textual data. Originally, we had a completely unstructured textual data. That's what we originally had. And we have managed to convert the unstructured textual data into a structured numerical form. So again, we started off with a completely unstructured textual data. Document one, document two, these were the two documents we had, totally unstructured data we originally had. And uh, we have managed to convert that unstructured data into a structured numerical form, where in rows and columns we are able to see the matrix representation. And now we can do our existing supervised learning, anything with this data right now. And this is the core part of NLP. Okay, the core part of NLP is where we are taking a completely unstructured data from scratch, and we are converting the completely unstructured data into a structured numerical form. That's the crux of it. How we are taking that unstructured data and how we are converting that seemingly unstructured data that we had into a structured numerical form. That's the basic idea. And once we are done with this, now we can use it to solve any kind of problem. Now we can go back and imagine I want to use this data set for sentiment analysis. I can go and say, hey, documents like document one correspond to positive sentiment. Documents like document two correspond to negative sentiment. These are the two different types of documents we have. So document one corresponds to sentiment positive. Document two corresponds to sentiment negative. We are able to see that. And this is your labeled text data that we have right now. So what we are able to see right now is the labeled text data. So document one corresponds to sentiment positive. Document two corresponds to sentiment negative. This is the labeled textual data that we see. And this is the supervised learning model that we can interpret right now. These are the features, and based on all these features, we can say, okay, uh, features like this correspond to. Uh, so features like this corresponds to sentiment uh, positive. So features like this corresponds to sentiment positive, and features like this corresponds to sentiment negative. So this is how we can represent this problem just like a supervised learning problem. The first part is you convert the data into a DTM or a document term matrix. This is the part where we are numerically representing our text data. Okay, so every row is a document and every column is a unique term. And we look at word counts. You can clearly see that the word is present in document one two times, and the word is present in document two only one time. This is the numeric representations we have got. So this is only the features, the X's. These are the Y's. So document one is positive sentiment, document two is negative sentiment, and we can now take this data and build a typical supervised learning model using this data. Okay, so now we can go and take this data and build a supervised learning model. We can say, okay, these are sentiment positive, these are sentiment negative, and we can build a normal supervised learning model using this data. That's the way how we can run this. So this is like your typical logistic decision trees, knife base, all these algorithms can be used. That's the idea. I hope this is absolutely clear. Everyone's able to relate to it, what it is. A lot of pre-processing will be required, obviously. Okay. So a couple of other things that will be needed to be done here is basically removing outlier, removing stopwords. Okay. Uh, so for example, uh, you will have to do some basic pre-processing on the data. What kind of pre-processing am I talking about? So one very common kind of pre, so one very common kind of pre-processing would be the so one very Common kind of pre-processing here would be the so-called removal of special characters. So whenever I see any kind of special characters that are present, I will want to make it a point to remove all the special characters. That is one kind of pre-processing that I will want to do. Remove the special characters. That's the idea. So whatever special characters that I have, so make it a point and remove the special characters. Because you might have a review data, and in the review data you might have some stars, some semicolons, some some exclamation marks. All these kinds of data will add no value to the overall analysis. If you think about it, ultimately we want to use this data set for a sentiment analysis. So all this data will add no value in the whole sentiment analysis part. It will not help you in doing sentiment analysis, right? So that won't be useful at all. So what we need to do is we need to go and remove some of these special characters. So wherever I see any instance of special character, I will have to make it a point and go back and remove some of these some of these things that correspond to these special characters. So go and remove it basically. That's the way how it has to be done. Okay. So yeah, that's the inference. Next, um, we have to go and remove stopwords. Stopword removal is also a very important and a very integral aspect of the whole equation. That is what we call stopword removal. And usually the idea is removing high frequency words that are present in most of the documents. So we have words like you, the, a, and all these so-called high frequency words which are present across most of the documents. All these high frequency words which are present across most of the documents. We want to go and remove all these so-called high frequency words. That has to be removed. That is referred to as stopword removal. Basically. Okay, so the removal of all these high frequency words is called stopword removal. That's the idea. Because they add no value in the whole analysis. Think about it. You, the, a, and now the presence or absence of these words will they will not add any value to the whole equation. That's the idea. Okay. If you have a word that is present, it will add no value to the whole analysis. Okay. Because even positive reviews will consist of the words you, the, and negative reviews will also consist of the words you, the, and. So they will not add any value. That's the inference. So these kinds of words can be safely removed from the whole equation. That's the idea. And the next thing that we do is we do lemmatization. Lemmatization is again a very simple idea where we convert all the different verb forms into the same base verb form. Like here you can see liking, likes, likely. All of these are different verb forms of the same word. So we go and convert into the same base form, which is called like. This is called lemmatization. Now again, what is the benefit of these two approaches? What is the benefit of text pre-processing and all this that we talked about? Like let's say something like a removing stop words or lemmatization. What the main benefit of this is that it helps you create a better quality DTM. Okay, it helps you create a better quality document matrix. That's the idea. Okay, so the quality of my DTM is better than we had before. Okay, so it helps in creating a better quality document matrix. That's the inference. That's the basic idea. And generally speaking, if you have a better quality DTM, then the features like whatever you are able to see uh, the number of features or the number of dimensions will be lesser. If you have a better quality document matrix, then the number of features or the number of dimensions will be lesser. Because if you're removing stop words and if you're lemmatizing your data, imagine instead of 4 features or instead of 4 words, only 1 word will be represented. You do not need to represent all 4 words. You need to only represent a single word in the DTM. Okay, so that's the whole idea of how lemmatization will come in handy. No need to have 4 words. You will only have a single word that will be represented. That's the idea of lemmatization. And stopword removal also the same concept. You don't need to have different words like stopwords can be ignored. You don't need to have hundreds of words in my DTM in that across the columns, but whichever words are not important can be easily removed. That is the idea once again. That's the inference actually. Now let's see a small example This is, and by the way, whatever I discussed so far, this is actually called a document term matrix. This is a particular term, sorry, this is called a bag of words model. This is a specific term that we use for it. And it is the most basic feature extraction technique that we use in NLP. Now, there are several other techniques. There are lots of other types of modeling that we do. So this is not exhaustive, but then I wanted to mention that this is one of the most basic approaches that is used. There are other approaches also that are in existence. This is one of the most basic ones. Let's put it that way. One of the most basic ones. Okay. Uh, very simple feature extraction approach. Problem is it completely ignores the grammar of the structure. The context or the meaning of the words are completely ignored here. Okay, I repeat again. The context or the meaning of the word. What does the word actually mean? The context or the meaning of the words are completely ignored here. That is one of the things to keep in mind. Okay, so the actual meaning of the word or the context or the semantics or the actual meaning of the word is completely ignored. That's one way to look at it. And that is the idea behind this particular type of words approach. So the meaning is completely ignored. Okay. All right. Just to further expand on this idea, one last pointer before we go to the hands-on. Look at this all. Look at this small example. I had washed my house. I had my house washed. Okay. So document one, review one. I had washed my house, and document two, review two. I had my house washed. If you look at both the documents and you find out the list of unique words, you will see that the number of unique words are the same. Okay. So the number of unique words are the same in both the cases. We have the same number of unique words that are present across both the cases. That is what we are able to see. But then they mean two very different things. Okay, they mean two very different things here. The meaning of the words are very different. That's the inference we are able to make from it. Okay, I hope this is absolutely clear. Everyone's sorted, everyone's clear with this overall. Now, with this in mind, let's move on. Let's get going and let's see a small demonstration. Okay, let's see a small demonstration on how we can do this in code. Okay, so the idea is very simple. We have to somehow, just like how we have done one-hot encoding, label encoding for categorical data. Now, why have we done about encoding techniques? Because we need to figure out some way to convert our data into a numerical form. Machines cannot process text categorical data. We had to figure out some way to convert it to a numerical form. That's why we did encoding. The same way we are doing, this kind of thing. Okay. And just to take you through the code, this is my data set, very simple data set we have. Uh, it's a Yelp classification exercise, Yelp classification case study. I will share this with all of you. And the data set is a Yelp data set. Yelp is like a company, servicing company, which offers different types of home services, carpenters, painters, all that stuff. And people can book different services on Yelp, and then they will rate the services, right? So you can book different services on Yelp, and then you can kind of get yourself rate the services. This is my data set. You can see very real world data I've taken from Yelp.com, and I've done some pre-processing and then share this file with you. Every row corresponds to one review. This is when the review was given, how much of stars the customer gave for the review. So this customer rated 5 stars for the service that was provided. This is the text the customer wrote. What was written in the review? This is the user who has given the review. And this is the business whom we have reviewed. Which business? What is the business? Is it a person? Is it a restaurant? Is it a salon? What have you reviewed actually? That is my data set. All that we are concerned about is only this and this. We are not concerned about the rest of the columns. So what we will do as part of the pre-processing is we will take the whole data and we will remove all the other columns and we will only deal with these two columns. This is my X and this is my Y. And this is very much in line with supervised learning now. We have lots and lots of input, output, or X, Y combinations. Okay, so text like this starts as this, text like this starts as this. We have got lots and lots of input, output combinations, and we will build a model. And next time we have a input text, we will try to predict what is the output stars. That's the way how we will solve it. Okay, so next time we have some input text, we will try to predict what is the output stars. We again have x and we have y. So this is the input x and this is the output y. So based on the text of the review, we are trying to predict what is the stars of the review. That is the problem that we are trying to solve. So based on the input text, we are trying to predict what is the output stars. So first things first, what we will have to do is we will have to take that text data and we will convert that into word counts. So the objective is to go through all the 10,000 rows of text we have right now. So we have the text column. So go through all the 10,000 uh, records that we have in the text column. Okay. So go through all the 10,000 rows that we have in the text column and find out what are the list of unique words. Okay. So go through all the 10,000 rows, and after going through all the 10,000 rows, we will try to find out what are the list of uh, unique words that we are getting. So that is the first thing that we will do. And the list of unique words are as follows. This is like your W1, W2, W3, let's say dot 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 W 10,000, something like that. Let's say this is so this is how we will represent our data in the form of a document term matrix. So we will go and represent our data in the form of a DTM, where every row corresponds to a document, every column corresponds to a corresponding term, every row is one document, every column is one unique term, is one unique word, and we will look at word counts. That is what we call a document term matrix or a DTM. I repeat again, every row is one document, every row stands for one document, every column stands for one unique word, and we are simply tracking the word counts out of it. So what you are seeing here are the word counts. These are the word counts that you're tracking out of it. Count of unique words. Okay, word counts. Now this is how we can represent our data, and after that we will do normal supervised learning. And patterns are like this correspond to 5-star, patterns like this 4-star, patterns like this 2-star, and so on. That's the way how we will write this. Let's see the exercise here quickly. Let us see this one in action. So once again, you can see what we have done. We have taken the X, we have taken the Y, text and stars respectively. Train test split. These parts are very similar. Nothing will be different here. This is just like standard machine learning. Just like normal machine learning, these parts are also very similar. So we have taken the whole data and we have split our data into X train, X test, Y train, Y test. And then we have done tokenization. And this is what we have done right now. Count vectorizer. This is the most important part. We have used something called count vectorizer. Stop words equal to English. What is the meaning of that? It means that I will use count vectorizer and I will use stop words equal to English. Okay, so count vectorizer is what I'm using. Specifically, which stop words equal to English. And what this will do is it will go and it will find out all the list of English stop words. Okay, so it will find out the list of all the English stop words. That is what it will go back and do. What are the list of English stop words if we go back and do for you? So we can use this to find out the list of so-called English stop words. It will remove all the English stop words. And then I'm doing vec.fit. Vec.fit will now find out the list of unique words. And then these are the feature names. And this is the dot transform. And this is how the DTM will look like. Let's take a look at it. So in a way, a fit transform is what I've done. And this is the final document term matrix for how it will look like. You can see every row corresponds to one document and every column corresponds to one unique word, unique term or unique token. And this is the DTM that we are getting on the whole data. You can start to see that these are not really great quality tokens we have got initially, but what it has done is it has actually taken all the unique words on the basis of space. So depending on space, all the list of unique words are being segregated here. And this is the reason I mentioned that the text pre-processing part is very important. It is very important to pre-process your text data correctly so that these kinds of challenges will not come. So that's why it is an extremely important idea to go and let's say pre-process your text data correctly. That's the idea. right? I hope this is absolutely clear, friends. You're all sorted with this, I hope. Now, let's put this in the context of the entire modeling part. We can do this manually. We can first take stopwords English, and then we can uh, build a multinomial line-based model, nb dot pitch, and we are calculating the scores. You can see this is one way we can do it. The other way we can do it is we can use a pipeline. Again, something that we have talked about in the class. So pipeline is where you can string together a series of different steps. And here, what are the steps involved? First, I will do count vectorizer. Okay, so what are the steps involved right now? So first, I will do count vectorizer. Take the entire text data and find out the list of unique words and represent the whole data in the form of a DTM. That is what count vectorizer will do. So count vectorizer will represent the whole data in the form of a document or matrix. And then I will go and do a multinomial lie-based model on the data. Two-step process. So count vectorizer stopwords equal to English. That means first remove all the English stopwords, lowercase equal to true, convert all the words to lowercase. So you might have small cat cat, capital cat cat. So what lowercase equal to true will do, it will go and convert all the words to lowercase. So if I have small cat cat and capital cat, what will happen? I can end up converting all the words to lowercase. Everything will be converted to lowercase. Everything will become like small cat cat. And then after doing that, you will now go back and build a multinomial line-based model. First step is uh, you do count vectorizer, convert the data to a DTM, and then you do multinomial line-based model. And you can able to see the results here. This will be very similar. So what is it doing behind the scenes? This is actually taking that text and converting that to a DTM. And the next part is actually doing the classification model. So the classification part is standard. This is the kind of stuff we have talked about. Training, testing, accuracy, confusion matrix. Why are there two classes? Because there are only two classes we have taken. We have taken only 1-star and 5-star reviews. And we can clearly see the performance of the model with respect to these two classes. Some very interesting observations, friends, that I would like to point out. First of all, it's a highly imbalanced classification problem. Why imbalanced? Because uh, there are lots of 5-star reviews, but there are very less number of 1-star reviews. Okay, so there are lots of 5-star reviews we are able to see, but the number of 1-star reviews are much lesser. So we are anyway starting out with a highly imbalanced data set. So the data set that you are having right now is highly imbalanced. So lots of 5-star reviews you have, but very less number of 1-star reviews you have. So highly imbalanced data we have to start with right now. That's what we have. And when you build a machine learning model on this kind of data, what kind of challenges will you typically see? So when we go and build a machine learning model on this kind of data, the challenge that we will see is the model will perform very well for the 5-star review, but the model will not perform very well for the 1-star review. So 5-star review, the model will do very well. Okay, so specifically for the 5-star review, the model will perform very well because there is a lot of label data we have for that, justifying that. But for the 1-star, the model will not do that well because there is not enough label data we particularly have for the 1-star. So that is why you are able to see the performance of the model is also much better for the 5-star, but it is not that well for the 1-star. The other reason is obviously because negative reviews are kind of much more difficult to estimate because there might be sarcasm and other aspects of speech involved in that. So sarcasm is also a very very important idea I wanted to highlight. So negative reviews often are extremely hard to detect because of aspects related to sarcasm. So this is what we are able to see. Two classes, 1 class and 5 class, and very clearly the performance of the model is kind of extremely poor. There it is. This is what we have here. You can see that every single row corresponds to a message, and we can see that the message is a spam or a ham. That's the inference we have, the information we have right now. Binary classification problem. And now let's get going. So first we do the count vectorizer. We convert our data into a DTM or a document matrix where every single row corresponds to a document and every single column corresponds to a unique term. And we look at word counts along the way, right? And this is the DTM or the document matrix that we are building in the process. Okay. Once this is done, now we go ahead and we build the SMS classifier. This is what it is, and we can see this in action. Okay. So yeah. Accuracy of the model, we can check what kind of accuracies we are getting. So I think as of now, we are getting a model which is coming out to be approximately 95% accurate. A pretty accurate model compared to what we have. Okay, now let's move on. Let's discuss about some aspects of the cloud related to what we have seen, and let me show you some other things. And particularly when it comes to the cloud, there are three main uh, companies that are involved. One is Google. Google has something called Google GCP, Google Cloud Platform. When it comes to AWS, AWS has AWS. Amazon has something called Amazon Web Services, that is Amazon's cloud, and Microsoft has something called Microsoft Azure, that is Microsoft's cloud. Now, cloud is a huge space. So right now you can see I am inside the Azure workspace. Inside that, there are lots of things we have. We have virtual machines and all these things we can create. So it's like a monumental topic. But what we are specifically focused on here is Azure machine learning. And or similarly inside AWS, if you're doing something, you'll be looking at AWS SageMaker. So that is what we are specifically focused on. So how do we use the AI ML based services inside these cloud environments? That's the part of the conversation we are having. Okay, so we'll click on create. We'll click on create new workspace. That's the first thing we will do. So Azure Path sponsorship. I'm going to create a new resource group. So this is the default resource group I will keep. Let me again call it demo 29 August and click on create. Okay, this will just take a minute. So I need to create a workspace. Workspace is like a directory or a folder you can think of. And it's like a resource also that you're parallelly creating. And using this resource, I will go and I will kind of perform some of the machine learning activities inside Azure. So wanted to basically draw the connect that whatever we have done in our local Jupyter notebook, how does all of those things connect with the big picture idea of what we have inside Azure? Let us see. It's going to take a minute to do the deployment. You can see deployment is in progress. It's going to take a minute. All right, now the resource is already created here. Let's move on. Let's see. And here it is. This is the Azure Machine Learning Studio we are entering into. Right. So this is that single platform inside which you can do everything related to ML. That starts with model development, model deployment, everything. And even you've got Jupyter notebooks that are available within Azure. Right. So what we have been doing until now is we have been installing Jupyter notebook locally in our system, and then we have been doing all the work. But here you have Jupyter notebooks that are available uh, right inside Microsoft Azure. Okay, you can see this is what it is. So this is the authoring environment. This is what I was referring to. There is a notebook section where many of the you can actually create a Jupyter notebook right inside Azure. So what is the benefit of doing this? What is the benefit of creating a some kind of a Jupyter notebook right inside Azure? What is the benefit of doing that? So the benefit of doing that is you can so the main benefit of creating a notebook inside Azure is you can basically leverage all the cloud resources. So unlike in this scenario where the Jupyter notebook is created manually, right? So here we are using our own local resources, right? So unlike the current scenario where we are using our own local resources, uh, we can go and use the cloud resources also. Okay, so we can now go and use the cloud resources. That is one of the things that can be basically done. The cloud resources can be leveraged. Okay, because our local machine is limited in its capacity, in its bandwidth, other kinds of things, right? Uh, so now we can basically utilize the cloud compute and the cloud resources for doing the task. That is something that can be done. So we can click on file and we can click on create new file. And once I click on create new file, you can see untitled.ipynb. So we can basically create a Jupyter notebook right inside the cloud. Very simple way you can do it. Pretty much all the stuff that we have discussed, NumPy, Pandas, all the Python programs that we have written, all of these things you can do right inside Azure. So you can clearly see that Jupyter is not just a like just something we have taught you. Jupyter is actually a very, very common um, you know uh, software that is present in many cloud environments. Even within AWS, you have got SageMaker notebooks. So Jupyter is a very, very popular development environment that data scientists use for model building. Deployment is a different ballgame. So once your model is created, the deployment part is done using Python scripts. That's a different ballgame. Now, let's move on. Let's see what else we have got here. We got AutoML. AutoML is like really cool. And what I will do is I'll show you a small example of AutoML here in action. And AutoML is the idea where we can go and uh, we can automatically go and create a workflow. So all this while we have done the things manually, right? You get some data, you do the pre-processing, do the EDA, and you perform the entire thing manually. But with AutoML, what we can do is we can go back and with AutoML we can go back and let the machine automatically do all of it. So let me show you how AutoML looks like. So I'll just set up a new experiment called demo, and I will quickly go ahead and select the type of task. The type of task will be, let's say, I'm just going to take a basic exercise here. This could be like a regression problem. We can take the example of concrete that we did today. So we can take regression, and I'll click on create. I'll to create the data set here. And the data asset name will be, excuse me, concrete demo. There it is. And concrete, let me call it concrete only. It's a tabular data. That's okay. Click on next, and from local files, and I want to go and upload the file. Okay. So very simple. I'll upload the file. All of you can see. Click on next, and this is the part where Azure is creating a data asset. It's creating a data set, and this is a kind of the data set which I have uploaded. We have all the 8 different features of concrete, and based on that, we are trying to predict the strength of concrete. That's the output column. The last column that you see right now is the concrete strength. Okay, so the last column that you see on the screen right now, that stands for concrete strength. So that is what we are able to spot. The strength prediction is what we are trying to do. So click on next, and I think other things are fine. Click on next, and finally click on create. So I'll click on next again. Target column will be strength. Strength is what we are trying to predict as target column. You can do some other further settings right now, featureization settings. You can specify what types of feature engineering things that you want to do. So you want to do some log transforms, normalization, all those kinds of things you can add in here if you want. So you can specify, otherwise you can leave it as default. So validation type is automatic, that's okay, and test data will be train test. Straightforward. I think you can start to see very, very simple. Serverless GPUs are not required because this is going to be standard machine learning. And I will procure a very low cost virtual machine. This will cost me $0.29 an hour. And on this machine, I will run my task. See, there's nothing required. All I did was load my data, specify what is the output column, and that's it. The machine will take over. It will automatically do everything behind the scenes. So click on next, and I will click on submit the training job. And once this is done, you can see that stuff will happen. Submit the training job. Let us see. And this is going to happen behind the scenes now. This is how AutoML looks like. There's nothing that I have to do. The system will take over and it will automatically try different experiments, different permutation combinations. It will try out behind the scenes. And at the end of it all, it will give me uh, the best model. That is what it will do behind the scenes.
So how long will this process take, sir?
This you can actually limit it, but right now I think generally it might take like an hour or so. Yeah, but you can limit it. You can put some constraints and you can limit it also. But right now it will take an hour, and you can also monitor the progress every time it tries out a different algorithm
Mm.
and all that. You can actually monitor what kind of accuracies we are getting. So it tries different experiments, and for the different experiments it tries, it shows you what is the accuracies it gets. Yes.
Mhm.
So
Okay.
what I'm showing you right now, friends, is this is running. You can see it will take a while to complete now, and all is very simple here actually. So once you this is the Azure environment in which I'm showing you AutoML, but there's similarly a lot of other so-called AutoML tools out there. Something where you guys can also do it. Like, see, if you have to use this, then you will have to have an Azure subscription. Now the question is, sir, what is the case if I don't have an Azure subscription, right? So how do you guys get to use it? So if you want to try it out a little bit, you can, if you want to try a flavor of AutoML, you can go and you can navigate over to this particular site called um, Aquarium. And Aquarium gives you access to something called H2O AI, Driverless AI. This is a company, and this is again a completely free thing that you can use for 2 hours, limited to 2 hours. But I think it's good enough for you to get a flavor and taste of what AutoML is. So in case some of you are interested, you can click on this. You can click on create a new account. It will take you hardly 10 seconds to sign in. Click on login. Once you click on login, you can see a list of labs. Click on browse labs. This is the list of labs you will find. There are a lot of training labs that they give you, and all of these are free. This is just for student access. Okay. And the one that you can click on is the first one, which is, let's say, driverless AI test drive. This is again a AutoML product that H2O has. Click on that and click on start lab. It takes a while to start. And here again, you can do something very similar. You can take the same concrete data set, you can upload it, and then you can just run it, and you will see a series of different things will happen, and the model will get created. It will take a while to start actually. We can just wait for a minute, and then here also you can see parallelly the AutoML job is still running, and after a while it will start to show the different iterations it has gone through. So right now it's still just started here, and after a while, once we complete a few experiments, it will tell you that hey, I tried gradient boosting and I got this much accuracy. I tried random forest and I got this much accuracy. You'll start to see those numbers coming up after a while. Okay. Just wanted to take you back. This is model training happening now. You can start to see running execution. You can start to see that it will give you the progress also. So right now the model training is happening, and after a while you will start to see some of the outputs and some of the log information will come up. This will take a while. This will take at least a few hours to run. As I said, you can restrict those settings also, because remember there is a cost that you're also incurring here as well. Okay. And coming to Aquarium, this is the thing that is just starting up now. And I think while these two things happen, let me show you some other things also in terms of designer. So we talked about notebooks, we talked about AutoML, and now finally I'll take you to the designer view. And by the time I think I complete this both of them will be active. Okay, let us see. So you can create a machine learning model using AutoML, no coding involved. This is again really cool. This is where you can actually create a machine learning model using just drag and drop. I mean, I know it's probably eye opening, but just to give you an idea to you, what's happening in the world of AI today, we are increasingly seeing a lot of these so-called low-code, no-code AI tools that are mushrooming. This is one such example. And once again, you can see I'll take the same concrete data set, but just that here I will create a workflow, but I'll do it in a very visual manner. No need to write any code. So first I'll take concrete, and then um, I can go ahead and kind of do some scaling. So let's do some data transformation. Data transformation. The tons of data transformations we have got here, and you can see you can just add in some transformation tasks that you want to do. Scoring, text analytics, model training, statistical functions. So tons of different things that we can add here. This is data transformation. Once again, math operations, clean data, convert to CSV. All these are the different stuff here. But this is normalized data. If you want, you can add in this step also, and see how we are connected the arrow. After this, what I will do, train test split. So train test split is the process where we take the data and we split our data into training and testing. So we can do a train test split also. And finally, what we will do is we will go back and build the models on the training data, and we will evaluate the models on the unseen test data. Okay, so that's what we will go back and do right now. So I will take the split data step here. Whatever output I'm getting from transform data, I'll take that, and first I have to configure that actually. Let me go and configure. I'll do a z-score transform, and what all columns we want to transform, I'll select all the columns, edit columns, and select all columns. So I want to go and transform all the features. Features means X's. You'll only want to transform X's, not Y's. Okay. Once this is done, go and connect it here. And in split data, 70% 80/20. Okay. And what will happen? What will happen here, friends? Let us see. So we will use the machine learning algorithm. So split data, first of all, you can set the percentage. So I think this will be 80-20. 80% of my data is this side, 20% this side. See how easy it is to configure these things without writing a single line of code. And it's a regression problem. So I will probably choose linear regression to start with. Okay, so we have the data. We will use the algorithm. So we have the data, use the algorithm and build a model. So I will come to the train model step. The train model step, drag and drop that here. Okay, you can see right now we have the algorithm that is linear regression dot fit x train comma y train. This is what is happening in the code behind the scenes, right? So we have the LR algorithm. We are doing a dot fit of x train comma y train. So double click on it, specify the target column. You can probably just take a look at the target what it is. I think so. Right click and click on preview data. If you click on preview data, you can get a very nice visual depiction of what kind of data you had here. Data profiling is also automatically done. Basic histograms and skewness, all those computations are automatically done. So the output column is strength. Let me select that. So come all the way to the train model step, label column, and label column is going to be strength. That's it. Click on save. And now we are ready. And now the final step after training is model evaluation. So we'll come to uh, the model evaluation part. So after training the model, I want to go and score and evaluate the model. So two-part thing we will do. First is score model. So first we have done algorithm.fit x train y train, and whatever model we have built, we will do dot score of x test y test. Okay, so we will now go back and take that train model and do a dot score of x test comma y test. See how we are connecting this test set now. So whatever model we are getting, whatever linear regression trained model we are having now we will use that model and do a dot score of x test comma y test. Okay, so we will get the predicted values. Score means we'll get the predicted values, and after that we will click on evaluate model, and evaluate model will simply do a comparison of predicted and actuals. There it is. This is a simple workflow that I created here, starting from getting the data, normalizing, splitting, building the model, and scoring on the testing data set. So get the predicted values, and evaluate means compare the predicted with the actuals to calculate R square. Very simple. After you're done, just click on configure submit, select an existing experiment, and you have to create a compute runtime also. So compute cluster, I think we have got one cluster that is active. Let me just check that. So we are all set, and you can see that right now my compute is succeeded. It's running, and now I'll simply go back to this environment and go ahead and quickly select the compute instance. Okay, so select the instance and just go and click on review and submit. Okay, so now you can see that the pipeline will start execution, and we can click on this pipeline job is submitted, and then we have nothing more to do. We just authored it. We just did the development. We created this pipeline, and now it is getting executed here. Click on job details, and we can actually see the whole pipeline in action. So the complete pipeline will be in action now. So you can take a look at it, and we can see the complete pipeline in action now. We can just zoom out a little and see what's going on. I can see the pipeline job is executing right now, friends. You can already start to see it's running. After a while, you can see it will be successful. Once you see the green tick would mean that it's successfully executed. This is just one thing I wanted to show you. Okay. So yeah, so I think AI tools are getting a lot more advanced. You'll be able to create these workflows a lot easy. You can see that it's green now. Green means it's successful, and after that you'll be able to see that the final step once it completes model evaluation, all that we'll be able to see. Just wait for a while here and see how this completes. The AutoML job is also running, and if you want to see what all jobs are executing now, you can click on the section here, and you can basically start to see what all jobs are running now. Click on the jobs section, and this will give an idea to you what all jobs are executing. All jobs, and this is the jobs that are running right now. This is that AutoML job that is running. You can see, and this is the pipeline job that is running right. So both these jobs are executing right. All of you can see. Okay, this is how the interface looks like. That's what I wanted to mainly show you, the interface, how it looks like. Okay. And you can see the AutoML job, it's running, model training is happening. And this is what I wanted to show you. It's actually showing the iterations. It's gone to 20 iterations now. And in all the iterations, it's showing you what is the algorithm that was used, XGBoost, LightGBM, all that. what is the name of the algorithm that was used, and it also tells you what kind of scores we got out of it. So what is the name of the algorithm, and also what kind of scores we kind of got out of it. Even that we are able to infer, right? So you can start to see how we are able to get it. This is still running. It will take a while to complete, and the pipeline we can again say it is completed now. Train model is until that is over. Until train model is over, last two steps are remaining. Scoring is happening, and evaluation will happen after that. So once that is complete, I'll just show you the preview. What is the scoring that has happened? But the objective here was again not to teach you Azure, but objective is basically to show you how simple it is to perform these kinds of tasks inside the cloud environment. Okay, so this is the last thing that will happen now. Let me show you that as well. All right, and now once it is done, you can right click on it and you can click on preview data. And once you click on preview data, you can actually see the overall preview, and you will be able to see the you'll be able to observe the the R square of the model. So, and you can see the coefficient of determination is coming out to be 60%. I think we agree, all of you agree with me that the baseline linear regression model on the concrete data set indeed gave us around 60% R square. So we're getting the same results here with the pipeline. Different ways of doing things, but we didn't use any Jupyter notebooks here in the process. The same way we have Aquarium. Now the link has come up. You can see this is the same one, Aquarium H2O. This is something that others can, you guys can all use. 2-hour free trial that you get. You can click on the link. It will take you to the driverless AI environment. Add the data set here. Files. Upload the file. File that I will be uploading here will be concrete.csv. Once again, the same concrete data set I will take. There it is. And same steps. Very, very similar kind of steps. So we'll just click on it and just click on predict. That's it. Straightforward. Give it a name, demo. Specify the output column. The target column is going to be strength. And that's it. That's it. I'll reduce some of these numbers so that the training takes less time comparatively. The scoring metric will be R squared, and launch the experiment. So there's your driverless AI environment. Okay, how cool it looks. So this is the future, guys. Okay, so what you're seeing right now, it probably is. I know it looks very scary, but this is what it is. This is where things are headed, where machines will take over, and data scientists, as we know it, doing all these mundane tasks, we will not be needed, honestly. Yeah, but one thing I believe in is our roles will evolve. And not to scare you saying that, okay, all the jobs will go away. Not really. But our roles will evolve. We will evolve into better roles, more functional roles, more domain specific roles. Those are the kind of things that will happen a lot. But the plain vanilla, mundane data science development that we have been doing for ages, that's going to definitely stop because you are already seeing these machines are able to give you exceptional results. The main challenge, I would say, is the interpretability, the explainability. Those are some of the reasons why companies are still very, very reluctant to use these kinds of tools.